first let me answer some questions asked by students. This is a Bowman-Welch algorithm, basically the EM algorithm for hidden Markov model. So in this notation, my x is a vector, x1 through x capital T or x1 through xn, which is an observed data sequence, the x, okay? By the way, I never seen you before in the class.
Yeah.
Okay.
I prepare for the interview.
What's it?
Preparing for the interview.
Okay. So now the reason we so what is this equality is about? Because we don't know the joint. We wanted to find out what is the likelihood for x given theta, the parameter, hidden Markov model. But we actually don't know the distribution of x given theta. We only know the expression if z is also given, the latent states. So how you write out what is the probability of x given theta? You have to sum over all the latent state z. So the left-hand side is the marginal distribution of x, and the right-hand side, each one of them is a joint of x and z. So to get the marginal of x, you have to sum over z, sort of integrate over the variable z. So the difficulty is, once you take log of a summation, when you take derivative, that sum will in your denominator, which is very difficult to deal with. Now here, in the EM algorithm, we actually pretend that we would know z. So we write, this expression here is basically one of the term inside the summation. We just know z now. But I purposely put z in uppercase because we actually don't observe z. So we will eventually integrate over after we take the log. Okay? So this for the EM algorithm. I finished my previous lecture sort of unfinished about some imbalanced data, the discussion, but I decided to switch to the classification tree because I want to make sure you learn enough classification tree so you can do your project and during the Thanksgiving break. So we have learned tree model before. Yes, good assignment. So you can do your shopping and then do your project. Because you need something to work on, midnight when you're waiting outside some department store. We have learned regression tree before, so I feel like this is a fairly easy task for us to learn tree again, but now our task is classification, not regression anymore. So 3 elements when we build a single tree, where to split. When I talk about split, I mean the variable j and the value s, we're going to do the split, and when to stop, and also how to predict as a final leaf node. And task 3 is actually very easy. Once you get to your leaf node, meaning that's a node, some observation going to be there, and you decide not to do any further split. And you just look at in that node, some of the data will be from class 1, some are from class 0. So you just predict with the majority voting or predict with a probability, which is the percentage of ones in that node. And when to stop, if you can remember what we discussed for regression tree, we're going to introduce some kind of a loss plus penalty criteria and use the so-called weakest link algorithm to find a single tree. It's okay if you don't remember the detail because a single tree won't work anyway. We're actually going to build a forest model. But the very important question we need to address is where to split. Because even if you want to build a forest, you still wanted to know how to build a tree, and that's the basic step. So how we decide which variable to pick and which value to split. At every split, we are going to define some quantity called the goodness of split criteria, or kind of a goodness of fit. Meaning we are going to try all the variable j and for all possible splits. And usually, if we have n samples, we only have n-1 possible value. We can split them into 2 groups. So we try all of them, and for every combination, we're going to look at the value and this criterion phi, and then just pick the best one. And the best one could be the one give the highest criterion or the lowest, depending on how you define your criteria. So we know for regression, we actually evaluate the goodness of split by looking at, well, if we split at variable j at value s, meaning we divide our data into two groups now, left and right. We divide them into two groups, and we can calculate, for example, if we don't do any split at the parent node, what's the corresponding residual sum of square if we predict with the average from that node, right? So suppose we have 20 observations here. We can look at the average, and we can look at residual sum of square if we predict with the average of the 20 observations. And then we can look at if we do, if we're going to apply a split, divide the data into two groups, 15 on the left and 5 on the right. And again, we're going to predict with average for all the observation in the left node and the average of all the observation among the 5 on the right. So we have two mean values now. So we do our prediction. We can calculate what is the residual sum of square, which is a cumulative residual sum of square from the left and the right, right? And we know that the new residual sum of square is always smaller because you sort of add a new variable. And we look at the difference, sort of the reduction of, deduction of residual sum of square, for the split. And we try all possible splits and pick the one gave us the highest deduction. And we do that split, okay? So that's for regression. And let's see how we're going to do that for classification. For classification tree, we're actually going to check the gain of the so-called impurity measure. So what is an impurity measure? You can think about just a binary classification. And a node is pure, meaning in that node, we only have observations from one class. And that's good. That's the ideal scenario. And the impurity measure is going to be high, okay? So if we do a split, again, we have our node T, and we split into left node and the right node, okay? Again, we could have 20 observations, and we have 15 on the left and 5 on the right. In general, we can define something called impurity measure, and it's denoted by a lowercase symbol I. Well, actually, it's capital I. It's uppercase I. This is our impurity measure. So impurity measure basically is going to take a probability vector of length k. And maybe let me talk about the impurity measure first. So it is a function over a probability vector, p1 until pk. K could be 3. Let's talk about general case. That means you have 3 classes, and you can talk about what is the probability over the 3 classes. So p1, p2, p3 will be 20%, 30%, and 50%, right? So it's a probability vector. Sum always equal to 1, and every entry is always bigger equal to 0. And then we want the impurity measure. Ideally, if we want a node to be pure, we actually want the impurity measure is to be small. So this impurity measure is going to achieve the maximum value if your probability over the k classes are equally likely. Okay, so if the probability vector is 1 over k, 1 over k, 1 over k, then you want that function I give you the largest value because it's really not pure. Okay, and you want this impurity measure to be smallest if you actually only have observations from one class. So small minimum occurs at one of the PJs equal to 1. That means all the other PJs will be 0. So that's very pure, means the opposite of impure. So it's going to be small. And our impurity function usually is a symmetric function because if you, if you have a percentage distribution, 40% versus 60%, and which is the same impurity if you do 60% versus 40%. So it's symmetric. if you shuffle those probability vectors. So ideally, when we are doing classification, we want the impurity measure for every node to be small. So it's like impurity the same as residual sum of square now. Okay, so once we know the impurity measure definition, let's go back to look at how we look at the gain or the change of the impurity measure. At every node T, the parent node T, we have some observation 20 are there. We can look at the empirical distribution over the K classes, and we plug into this impurity measure. So we get our impurity measure at node T if we don't do any split. And then we do our split, and now we have two nodes now, the left node and the right node. And then we can again calculate what is the impurity measure at the left and the right, okay? Now we cannot do simple summation now, because the impurity measure is not cumulative. It's more like a description at the probability level. So we have to do a weighted average. So in this case, if originally 20 observations split into 15 versus 5, then the weight for, so this one is going to be 25%, because 5 divided by 20. Because 5 observations out of 20, oh, sorry. That one is, the P sub L is going to be 75%, right? Because 15 out of 20 are located on the left. And then PR, which is the weight we assign to the right node, will be at 25%, because 5 out of 20 are located to the right node. Agree? So this is how we calculate the change or the gain of the impurity measure. We have our impurity measure if we don't do any split, and then we calculate, and if we do the split, and we do a weighted average of the impurity measure from the two nodes, and we look at the difference. And we will do this split, we pick the split that's going to give us the highest gain of the impurity measure, which is the biggest deduction of the impurity measure. Okay. So let's take a look of some examples of the impurity measure. One is misclassification rate. So if we do majority voting, what is the misclassification rate? If you have 3 classes, and you calculate what is the observed frequency of the 3 classes at this node, and suppose the node 3 is the most frequent one, so you're going to predict everything to be from class 3. So the error would be P1 plus P2, right? Because it's going to misclassify the other 2. So the misclassification rate is always equal to 1 minus the percentage of the majority group, because that's a group got correctly classified. Okay. So let's look at whether this is a good impurity measure. Well, apparently it will achieve the maximum if even the maximum is only 1 over K. So you can actually go back to check whether it satisfies those conditions. The maximum achieved when they are equally distributed over the K groups, and the minimum achieved if one of them is equal to 1, because if one of the PJ is equal to 1, then the misclassification rate is actually 0. So that's right, because one of the PJ is 1, meaning in this node all of the observations are from one class, and you do your majority voting, everybody get correctly classified, so error is 0. Okay. Good. And it might be easier just to focus on the case where K is equal to 2. So misclassification rate will be the minimum of P or 1 minus P, which is the same as 1 minus maximum of one of the 2 numbers. Another another impurity measure is called entropy. So entropy is for two classes will be P times 1 over P and the other thing. Another is the Gini index. I give you 2 different expressions for the Gini index. So from the left-hand side, you can it's easier to see that this is a symmetric measure because it doesn't matter how you can randomly permutate those PJs, it should give you the same answer. Okay. So there are 3 different criteria you can choose when you build a tree. The recommendation is when you try to build a tree, you want to use either entropy or Gini index. They actually behave very similarly because they are both concave function and strictly concave. So you can, when you build your tree, you want to use those 2. But when you go back to prune your tree, you can use misclassification rate. So why is that? Let me show you the result, and then we can come back to explain the difference. So I attached the R code for analyzing the spam data, and when I talk about regression tree, I think I use a different package called the RPart, recursively partition. But here I use tree model, and they are very similar. So let's look at the. You can check I'll leave this as assignment for you guys to read and figure out by yourself how to use this package to fit a classification tree. So let's just look at one of the tree, which is here. Okay. One thing you realize is, I cannot draw anything here. Let's look at this split. You do a split, and your prediction majority voting on the 2 nodes are all 0. The same. Meaning you take a group of data, you split them, and majority voting is the same. So now, question is, if I want to use misclassification rate as the evaluation, do I have to make the split? What is the gain of the misclassification rate? Should be 0, right? Because on both sides, the majority are from class 0. That means if I merge them, don't do the split, the majority is still going to be the class 0, and the misclassification rate should be the same. But why the algorithm actually going to do this split? Let's go back to look at a particular calculation. So let's consider a binary classification problem, and let's try to evaluate the following split. I denote it by this way: 25, 5 is going to divide it into 10, 0 and 10, 5. What that means, I have a parent node, and he's a parent, and it has 20 samples from class 1 and 5 samples from class 0. And then there is a candidate split. It will split the data into 2 nodes. And in the left node, there are 10 samples from class 1 and 0 samples from class 0. And another node is 10 from class 1 and 5 from class 0. So this is an example you're going to find out if I do majority voting. Even at the parent node, the majority will be class 1. In the 2 child nodes, left and right, the majority is still class 1, right? So the classification rate should be the same, and we can actually evaluate the misclassification rate. So this is the misclassification rate at the parent node. So 5 out of 25 get misclassified. Agree? And then those 2 probability is the percentage of the sample in the left and right, which is this PR and PL, right? So now we're going to do. So we know the misclassification rate at the parent node is the first entry, and then we have to minus the weighted sum of the misclassification rate from the left and right, and the weights are 10 divided by 25 for the left node, and 15 divided by 25 for the right node, right? And then let's look at what is the misclassification rate at the left and right. For the left node, it's a pure node, so misclassification rate is 0. And for the right node, we're still going to misclassify 5 of them. So the misclassification rate is 5 divided by 15. As you can do the calculation, you're going to find out the gain is 0. Meaning, if I don't do this split, the misclassification rate is the same. So from the parsimonious principle, we shouldn't do this split, right? If I use misclassification rate. Now, if you agree with the calculation for the misclassification rate, now if we use entropy, the first bracket is entropy for the parent node, right? Because for the parent node, you can think about parent node is basically a probability distribution over 2 outcomes, and the chance of saying 1 is 20 out of 25. So, well, basically those are the 2 probabilities, and log is the reverse of the probability. So that's the entropy for the parent node. And then we should calculate the weighted minus the weighted entropy from the 2 left and right nodes. So that's it, the weights as what we calculated before. Now for the left node, because it is a pure node, you can find out the entropy is 0. Yeah, why the entropy is 0? So we have to calculate what is the entropy for a probability vector 1, 0. So you're going to do 1 times log 1 plus 0 times log 1 over 0, right? I mean, 1 over 1 is just 1. And the first term is 0, right? 1 times log 1 is 0. And 0 times log infinity, that infinity is of order 1 over 0. This part should also be 0, okay? So if you get a pure node, entropy is 0. So that's why we have a 0 for the left node. And then you can actually calculate what is the entropy for the right node. And you can check this at home. You're going to find out the difference is actually bigger than 0. So in short, if you use entropy or Gini index, because they're strictly concave, it will favor splits that will lead to pure nodes. What's this strictly concave mean? Let's look at the binary case. Oops. So let's look at binary. Because the binary, we only all those impurity measure basically is a function of just the p, because the other case just 1 minus p. So you're going to find out the let's draw what the. So this is a P. What is a misclassification rate? This is pretty thick. Size. So what is this? So this is 0, 1, and 2. Oh, sorry. 0, a half, and 1. So what does misclassification rate as a curve of P, what it look like? Right? It's just like a tent. And the height is a half. Because remember, it's a minimum of P and 1 minus P. Right? Because this is a misclassification rate. Okay? So if somehow when your 2 nodes, when you do your split, if your prediction on the 2 nodes left and right are the same, in some sense what you're doing is you are basically have your left and the right are in terms of the probability of the percentage p are on the same side of this, on the left or on the right hand side of half. They're on the same side. Because this is strictly a linear function. So you do a linear combination is the same. So this is why if you do misclassification rate, if your prediction is the same, that basically means you gain nothing by doing that split. But for entropy and Gini index, they're actually strictly concave. So the curve look like this. It's a bit exaggerating, but let me just only draw one side, okay? So it's actually a function look like this. So it's a bit too concave. So it's something like this on one side. The other way is like this. So that's what the either entropy or Gini index will look like. Now, if you have a concave function, that all on this side, so you have two location means the percentage of the left and right in terms of the p. Then if you do a let me draw a piece of that. So if you have something here and here, if you have a concave function, in some sense, what you are evaluating at your parent node. So the two blue. Let me do it here. Okay. So I have 3 dots there. The 2 blue bars represent the percentage of the left and right in terms of the percentage, and the pink bar in the middle should be the percentage of the parent node. Okay. Then when you evaluate your impurity measure, you're going to find out something like your impurity measure is you have a weighted average of so P of let me do it this way. So it's a P of I think it's easier for me to draw on the blackboard. So you have your concave. So you have your when you have a split, they give you the same. The majority voting the same. That in some sense just mean I'm just do 0. That means both of their percentage is actually on the left hand side of a half. So this is a percentage of P right, P left. So when you calculate your impurity measure, let me do W right and W left. So W right and W left represent for the right node, what is the percentage of 1 in this node, and this is what is the percentage of 1 in this left node, right? And then you're going to find out, because of they are basically you can find out your what is the percentage at the parent node, the original one, is equal to P of I can explain why this is true. So the P sub R and P sub L is basically the percentage of how many total sample go from the parent node to the left and to the right. Okay, so you can find out your percentage of ones in this parent node is a weighted sum of the percentage of ones on the left and the right. Agree? Because so when you evaluate, so that's something in the middle. So when you evaluate your impurity measure, so this is the impurity measure for the node T, and this is the impurity measure for your left node. This is the impurity measure for the so this is for the right, this is for the left. Okay, and so when it is a concave function, you can find out the weighted average. We calculate when we do our comparison. We look at this the impurity node at the parent node, and minus the weighted sum of impurity node from the left and right. So there's always a gap here, positive gap, because of concave function. Okay, so just to summarize, there are different type of impurity measures. Misclassification rate, entropy, and Gini index. When you're trying to build a tree, and it's always recommended to use entropy or Gini, because that metric tend to favor pure nodes, and so you try to get a pure nodes, because otherwise at a certain point the misclassification rate would feel there's no improvement to do any split, but entropy and Gini can always find a way to keep growing your tree. So you can always grow your tree, use this entropy or Gini, but when you start pruning your tree, it's okay to use misclassification rate.
Is there like a general rule on where you should use entropy versus when you should use
Gini? I think they actually behave very similarly. I often use entropy because the underlying, the kind of a probability statement.
Okay.
Yeah. Any questions? Okay. So that seems like the only thing you need to know, and then all this stuff you learned before for regression tree just can be applied here, right? You know how to once you know how to work to split, understand the underlying criteria they use to split the tree, you can grow a tree, and you can stop when the tree is big enough, and then you can apply some pruning procedure, and then you can get your final classification model. Of course, we know that a single tree won't work very well, so we can do random forest, and similar idea, and as what we have learned for regression tree, and we can also do boosting. So here I wanted to explain the idea of boosting, because this very first boosting algorithm called AdaBoost was introduced in the context of classification. And so we're going to try to understand what exactly an AdaBoost does, and what can we say about the final classifier from the AdaBoosting algorithm. And then we're going to try to understand that AdaBoosting is basically just a greedy algorithm, and try to fit the model with so-called exponential loss. So let's first go with AdaBoost. When we talk about AdaBoosting algorithm, we have to switch to the notation we used for SVM. Our binary label y, I'm going to label it as 1 or minus 1, not 1 or 0. Okay, so our label will be 1 or minus 1. And our classifier, any classifier G, is actually only output the labels, hard classification, 1 or minus 1. Okay. Usually we focus on the so-called weak classifier, in the sense that we don't want to try too much to pick a good classifier. As long as your performance is slightly better than random guessing, that'll be fine. Actually, we can even take a classifier that's even worse than random guessing, meaning your error is bigger than half, because that's easy. You just flip the label, you predict it with minus G, and that means you're going to be better than random guessing. You're going to find actually boosting will automatically uses minus G. But when G is exactly equal to a half, indeed there's going to be a problem, as you can find out. So the goal is to try to find a way to combine those kind of weak classifiers to improve the performance. So what's sort of the overview of the algorithm? We're going to sequentially modify the weights on the N training data. So W1 through Wn, those are the weights we are assigned to the data. We're going to sequentially update this W. And then at teeth iteration, we're going to assign some weights to the N data points. And then we're going to pick a classifier. And actually, we can just randomly pick one. And then we're going to iterate the first two steps. And at the end, we're going to output some weighted sum of those classifiers. And the alpha, I haven't told you how to define alpha yet, but this is sort of the general framework. So two things we have to determine in our algorithm: how we do the reweighting and how we come with the final weighting alpha on each classifier. Clear so far? Good. So here's the algorithm. We're going to start introducing a superscript on the W, because we have to talk about iterations. At every iteration, the weights will be different. So we initialize our weights for every observation. Everybody is equally weighted with weight 1 over n. We have n samples, and then we're going to start our loop. At time t, we're going to either fit a classifier or just randomly pick a classifier. Which could be classification tree with only like 1 or 2 splits. And so that's our G sub t. So it's a classifier. And remember, G sub t only output 1 or minus 1. And if the classifier outputs something else, we can always do some thresholding to make the output It's only 1 or -1 the label. And then we're going to count for this particular classifier G sub t, we're going to compute the training error on the n observations. So usually the training error, we just look at the how many points got misclassified, which is why I is not equal to GT and XI. But now remember, our data are weighted differently. So our classification, when we look at the misclassification error, we shouldn't just get the counts and normalize by n. Instead, for every observation I, and the error is weighted with the corresponding weight for the ith observation at the tth iteration, right? So we can calculate the error, and the error is the error at time t or iteration t, so epsilon t. So epsilon t is going to be some number between 0 and 1. And then we're going to compute alpha t. Alpha t is a half log of that ratio. So usually if the error is bigger than a half, alpha t is negative. If error is less than a half, then alpha t is going to be positive. Okay? And also if your error epsilon t is very small, then alpha t will be larger, right? So this is alpha t. That's the one we're going to use at the end when we weight our classifiers. So we pick a classifier, calculate the training error, calculate this mysterious alpha t, and then we are going to update our weights. How we update our weights? And this is the weight we assigned for the ith observation, the current weight. And then we're going to times some number. You can actually ignore the zt because zt is just a normalizing constant to make sure the sum of the left-hand side, if I sum over I, will be 1. So it's a constant for everybody, for every I. But let's look at how we change the weight. Oh, this is an awful color. Okay, so let's see how we change the weight. Oh, that's strange. Oh, cute. So if currently for this particular classifier, if we are making a mistake, that means this product going to be positive or negative. Negative, right? If this weight is negative, let's right now assume for this classifier our epsilon t is less than a half. Because otherwise you're going to find out what we basically use minus and the gt. So let's assume epsilon t is less than a half. So we're not doing something even worse than random guessing. So we know our alpha t is always positive. Okay? So that means then you can see for the ith observation, if we are making mistake currently at ith observation, we're going to increase the weight, right? Because exponential minus yi times dx. So we're going to increase the weight because this number is going to be bigger than 0. But at ith observation, if we're doing okay, that means this product is going to be positive. Now with this minus sign, we're actually going to decrease the weight, right? So this is how we modify our weights, which the modification is actually based on how well we're doing currently at this iteration on this observation. So if we're doing bad, let's just put more weights on this observation because we want to do better next time. If we're okay at this current observation, let's just decrease the weight, okay? Great. Then once we know, this is why I say you sort of can ignore the zt because you can just only look at the wt superscript, wi superscript t times that weighting, and then the zt is just normalizing constant. Basically, zt is the sum of this part over I. That's a normalizing constant. So make sure now this at the t plus 1's iteration, the weights will be actually weights, meaning the sum of them is going to be 1. So this is our algorithm. We just do this in sort of like effortlessly because, as I mentioned, you can just randomly pick a classifier G sub t. So we just do this. And at the end, you stop at uppercase T, and at the end, you can output your classifier is the sum of those lowercase t G functions, and they are weighted by alpha t. You sum them. Now, how are we going to use this to do the prediction? Because our y's are labeled as 1 or minus 1. So we basically, for new observation x, we just plug them into the summation and just check the sign. If the sign is positive, you're in class 1. If it's negative, you're in negative 1. Okay? So this is the algorithm, and it's called AdaBoosting. It's quite surprising that the simplicity of the algorithm, but what this algorithm is doing, what does it mean that it actually can boost the weak classifier? So we wanted to show that the training error will go to 0 when my t is going to infinity, meaning we just run our algorithm, I set my t to be very large. Eventually, I can push my training error to go to 0. Just do very well, even though individually every little g is sort of a lousy classifier. I have to be very careful what I mean by the training error, because I talked about weights before, right? So here's the training. So the weights you're going to find are just some kind of artifacts from the algorithm. And as somebody who's going to use this black box AdaBoosting, my weight never changed. Everybody should count it equally. My training error is basically 1 over n on every observation. I want you to look at, well, for every yi, I will look at if I use my final gt and uppercase G as a classifier, will my yi sign agree with the sign from that summation? Agree? So for the first line, this is just ordinary misclassification rate when we wanted to use G sub t as our classifier. Our G sub t just happened to be the sum of those stuff, right? So that's our ordinary classifier. Then this equality is trivial because yi is minus 1 and plus 1. So when I check whether the sign is the same, I basically wanted to take yi inside and see whether this term is negative. Is negative mean the sign doesn't look great, right? Because yi can, so I can take yi inside. So agree with this equality, okay. And then I wanted to upper bound this summation by just upper bound the indicator function. How we upper bounded an indicator function? Our indicator function is like this, meaning my input is z. If z is less than 0, so this is basically equal to 1. If z is less than 0, will be 0 if z is bigger or equal to 0. It's just my indicator function, right? And that indicator function can be trivially upper bounded by e to the power minus z. Why? Because when z is negative, e to the power minus z, your exponential component is bigger than 0. So e to the power something bigger than 0 will be strictly bigger than 1. Okay? Now, if your z is positive, e to the power minus z will be less than 1. Oh, sorry. It will be still bigger than 0, right? Agree with this inequality? Because your function is like this. The thing you wanted to bound is your function is equal to 1 if z is less than 0, and will be 0 if z is bigger or equal to 0. But apparently 1 is upper bounded by e to the power minus z when z is negative, because this part is positive now. And when your z is positive, well, 0 is always upper bounded by any positive number, right? So it's a very trivial upper bound. So the indicator function can be upper bounded by exponential. This is what I call called exponential loss. Right. So you get something like this. And then you have this sum, and you have exponential. So let's see how we get this inequality, the last inequality. Here I just copy whatever I have here, the sum of 1 over n. So this is sum of 1 over n exponential and bunch of the sums. And every equality is in some sense trivial. So for this equality, you have sum over exponential that becomes product if I take that sum outside the exponential, right? And then this one is a bit it's not too difficult, and you have to sort of think about what this exponential. So this exponential actually appeared in our algorithm before. It's like, we have something like alpha t yi times the function gtxi. And that term, the exponential, appeared in our weight calculation. So you're going to find out the exponential component is equal to new weights divided by the old weights and times zt, right? So the numerator, this guy, is basically equal to the new weight divided by the old weight, t, and times the normalizing constant zt. Okay? So this is what I'm doing here. And also I changed my 1 over n to be wi superscript 1 because 1 over n is the weight we use at the very beginning. And then you're going to start expand that product. You see some nice cancellation going on, right? So you're going to find out this guy cancel with this, right? So eventually you get something like this, sum over w. But now remember, w is a set of a weight, and the sum is equal to 1 if you sum over I. So this term disappeared. It's just 1. Okay? It's kind of a magic. But you can take some time and go back, look at the proof. So it's very not too easy. I think the magic thing is this kind of a trivial upper bound for the indicator function. So you're going to find out for the training error, eventually it's upper bounded by the product of those normalizing constant. Now the thing is, what is a normalizing constant? I will show you that normalizing constant for each of them eventually is less than 1. And well, that's where you're going to find out why I don't want something going to be classification error exactly equal to half. Because you can look at this. Let me just first look at the conclusion. So zt, just do some calculation. Also buried in the calculation how we get the alpha t. And so everything can just, you just plug in all the expression. You're going to find out zt is equal to this. Epsilon subscript t is the training error. Again, the training error is a training error at time t or iteration t where the error is computed by using the weights. So it's not ordinary, ordinary is not the ordinary 0-1 loss. It's a weighted 0-1 loss. But no matter what it is a training error, is a number between 0 and 1. And you can see this expression, the largest value is when epsilon t is equal to half. And that will give you 1. But as long as nobody is equal to a half, you're going to get a number strictly less than 1. And then you can find out what is the upper bound for your, that means the normalizing constant is always strictly less than 1. And then you basically show that your training error can be upper bounded by a product of those ones. This is why when I add 1 more t, when I increase my t, I basically time a number less than 1, of course, is decreasing, right? So this is why we can show that the training error is always, going to decrease. Now, give me 2 minutes. I'll just show you, and you can check the code, the boosting, right? So I actually code the AdaBoosting algorithm, which is, I always feel guilty to say code because there's not much you can code. You basically translate Very simple algorithm. But this is some step just to show you, this is at time t equal to 1. And we have our data, square is one class, plus is another class. And I randomly just pick a position to divide them into 2 groups. So my classifier basically randomly selected. And then those bars, the green bars or blue bars represent the original weight. At the beginning, everybody equally likely, so the same height. And then the purple, is this purple the right name or? Yeah, purple is the change of the weight. Okay, now you can see when the places when we're making mistake, because when I do majority voting, so I'm going to classify this side as square, the other side as plus. When I'm making mistake, you can see the purple weights are increasing, and so how you adjust things, and you can do this for a lot of iteratively do this. At the end, here's an interesting picture I want you to remember. What I'm plotting here is the red dots are the original training arrow. So no weighting now. So this is the training arrow if I only use the first classifier. It's like my capital T. So oh, I cannot draw here. And this is my training arrow for G sub T. And when uppercase T, if I stop at 50, this is the training arrow. If I stop at 100, this is the training arrow. Okay. And you can see the training arrow is actually not monotonely decrease into 0. Why? It doesn't conflict with our proof. It's the upper bound is monotone because we use that trivial indicator is upper bounded by the exponential loss. So that's something I want you to remember because it's in the quiz. The AdaBoost combine the weight classifier, blah, blah, blah. And the training arrow is not monotonely decreasing with respect to t. It's upper bound. And the upper bound is going down. Eventually, of course, going to push everything to going to 0. And also, you're going to find out our classifier actually is okay to have a very bad classifier with arrow to be bigger than half. Because when you're doing your calculation, you're going to find out your alpha t is negative. So basically, you just flip the label of your G sub t. And the last comment is the classifier returned by AdaBoost is definitely not guaranteed to have good performance on the test data because our goal, all we showed so far, is the training arrow is going to 0. And it definitely is prone to overfitting. And we have to do something like regularization or stop early to make the output to perform well on the test data. Okay, good.